Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, for all those who are into the computer engineering, we would like to tell you all that today we are going to discuss about type checking, and for this we have with us in our studio once again Mr. Sarfaraz Masood. Mr. Masood is Assistant Professor in Department of Computer Engineering, Jamia Millia Islamia. So dear friends, let's take advantages from his experiences and try to understand what type checking is. Hello sir, welcome to the EduSet lecture.
Thank you
once again. Welcome to the EduSet studio, and I hope that the way you have delivered your previous sessions, previous lectures, this session of ours is also going to be one of the most productive sessions. So
absolutely.
Over to you sir.
I'll try my level best. Thanks a lot. Good afternoon friends. Continuing our discussion on compiler design, and specifically we have till now talked about the initial three phases. That is syntax analysis, lexical analysis, syntax analysis, and then semantic analysis. So the previous of our lectures were actually discussing about semantic analysis, where we were trying to extract certain meanings from the various programming constructs. Continuing our discussion in this part, we'll now talk about something called type checking, which is another very important phase or task of a compiler, with which it tries to check the correctness of the program. And this phrase that I've used, correctness, it has got many dimensions and phases. So we'll try and understand in type checking that what all aspects we're talking about. To overview our lecture, today we'll try and understand the various terms, something similar to basic types, understanding type expressions and type systems. Definitely we'll like to know more about something called a type checker that we need to implement. We'll talk about a simple type checker, type checking for expression and statements that we normally find in a program. We'll also talk about a concept called coercion, and definitely we'll end up with some constructive remarks. I definitely deeply acknowledge the various sources from which examples and images have been used for the purpose of this lecture. Specifically, I've been talking about the Owl Minsaiti book that I've been following for this series. Okay, so the big question comes up, what is type checking? The main aim of compiler is to translate the source program to a form that can be executed on a target machine, that we have done in the past lectures. For this, we actually need to ensure the following things. So we have done lexical analysis. We've done the analysis of each component that we find in a source program in terms of the lexeme, in terms of their hierarchy, and now we were talking about the meaning of these components. So check that. So I mean, these are the following things we need to ensure before we actually move into the task of translation. Check that the source program follows the structure and semantics of the concerned language. So this is what I was talking about. So the structure should be the same one as specified by the grammar of the language. The semantics should be also of the same way as it has been described in the language. We definitely must maintain a symbol table, and we have been talking about this, that symbol table was initially started or populated by the lexical analyzer phase, and then it was largely because of semantic analysis that we started getting information into the symbol table. So this task of making entry into the symbol table will continue even more in this phase of type checking, because let's say we had some variable int a, comma b, comma c. So now is the time when once we have analyzed that the type of a, b, and c is integer, and then these a, b, and c variables that we have specified will be used in the programs. So now is the time that those expressions, those statements, their correctness have to be checked. So symbol table, again, its role will come into picture. We need to know the representation of values. We definitely need to know the flow of information of data between variables, and also the structure of the computations. Let's just take a simple example, a similar one that I was just talking about. Consider variable x along with its corresponding target code. So to generate the code for this consideration, compiler must answer these following questions. What type, kind of value must be kept in x? That's a very important question. We just said that x is a variable, but then we also know that these variables can contain a variety of information. They can contain integer values, they can contain some real values, they can contain some character or string values. So what actually is this x carrying? Because the way it is to be translated will be depending upon this information. Is x an integer? That's again a valid question. Then this should have been actually what is the size of x over here. What is the size of x? If x is an integer, then in what size? Is x a local or a global variable? If it's not a variable or an identifier altogether, is it a function? Because we also have functions in our programs. So we need to answer all these questions before we even think about translation of this code. Translation means, I mean, converting the source code that we got that was talking about this variable x to the target code that we actually expect. So we need to understand these things. Just by saying x is a variable, okay, I say a is equal to b plus c. So it seems pretty simple that the value of b and c will be added and will be passed on to a. So this is the kind of code that we want. But what if b is a character and c is, let's say, an integer? So in general terms, an integer should not be added to a character. That does not make any sense. So in this way, we need to identify what type is being referred by an expression, what type is actually being talked about by this entire sentence, the component in consideration x, a, b, c, whatever it is it actually a variable? If it's not a variable, then is it a function? And all these aspects we need to actually talk about. So type is definitely a very important information that we must sort out before actually going on with the translation. So we also have a column or an attribute type within the symbol table. I think we discussed about this thing in the last class, in the last lecture. So type checking is a process of identifying specific errors in the source program on the basis of some explicitly or implicitly stated type information. Type checking can be static. We'll talk about this slowly in the lecture. These can be static if done on the compile time. These type checking can be referred as to being dynamic type checking if it is done at the runtime. We have languages actually which can be referred as to strongly typed languages and weakly typed languages. We'll talk about them shortly. One thing very important that we can say at this very point is that not all checks can be done statically. So as I just mentioned on this level in the slide, that there is a type of checking that can be done at the compile time, that is called static checking. So it's saying that everything cannot be done statically. It's giving an example. For example, let's say I have an array of size 10 written as int a10, and I simply say this variable int I. So this I will actually act like a subscript to this. So at my code, I'm simply saying printf %d ai. That's it. I'm simply saying this ai. So at the compile time, I do not know what value of I will ever come into it. So I simply cannot know whether this thing is ever going to mean right or not. For example, if I say this is a10 and if I say print me the value of a20, so this 20 actually will be a value that will come to me at the runtime. So at compile time, I may not be having this value. So this checking may not be possible or may not be feasible at the static level or the compilation level. This is the very reason why some recent security concerns have cropped up about type checking. The pretty most common situation that we know is the buffer overflow vulnerability. We can look up into this problem. This is a very hot kind of a problem that is there nowadays. So it's actually basically because of this very situation that I am not able to check at the compile time that this I will actually be ever talking about a number that will be greater than the size that we have described. So we say this is a10, an array of 10 size, and we're talking about or referring an 11th location or 12th location. So that can be accessed, but that should not have been done. Some notable tasks that can be done or that can come under the umbrella of type checking. We can definitely perform type compatibility, which means that the compiler should report an error if an operator is applied to an incompatible operand. This is the most basic kind of checking that we can do, is that let's say we have an operator, on that some operands are to be there. We just need to check whether the operands that are being applied on that operator, they are fine or not. So this has to be defined in the semantics of the language, that on this operator these operands can be allowed. So if those are not there in the program, then you have to report an error. The other type of task that we can perform is a flow of control check, which actually means that if the control leaves a construct, then is there a place for it to go to? Making it simple, I would simply say that the moment I move out of a certain block or a construct, let's say there's a for loop or a while loop, and I move out of it. So is there actually a place where I'll actually go to after this loop or this construct is over. For example, the break statement in C, not enclosed within a while or a switch or a switch statement. So there is a break statement, but that is not written within a for, or that is not there within a while or a switch. I mean, it does not mean where do you want to go to actually. Then you can also perform something called the uniqueness check, which actually refers to the fact that each variable there in our program should only be declared once. A function or a procedure should only be defined once. Labels in the case statement should be unique. Definitely we can mark up this statement by adding that each variable should be declared once within a scope. The scope factor can be added to it, and within that very scope the function or a procedure should also be defined once. So I mean, within a scope I cannot have int a comma b comma a. So that will be hindering this uniqueness parameter. So labels in the case statement should also be unique. I mean, within that very scope, absolutely, we are talking about a case statement that has that very scope, and within that scope I should not have labels that are repetitive in nature. So as I was talking about an identifier in C. So this kind of a check can also be done, and this will come under the umbrella of type checking. Some name related case checks, the situation in which the same name must appear more than once or more than one time. A function or program names in printf in C. So these are the kind of tasks that we can expect to perform in type checking. A type system actually. Type, first of all, we need to understand what type is. Type is a set of common properties associated with each value of that type. So just think about it. I mean, we say integer is a type. So the moment we think about integer, we get to understand so many things about it. Let's say if I say a is an integer, in the Turbo C situation if I talk about, then a will have 2 bytes, its range will be so and so, and there's so many information that we immediately associate the moment we understand this thing, that the type of this very component is this. So there are a set of common properties, okay, so associated with a value with each value of that type. So a type system actually specifies the semantic of a valid program, creates a knowledge base for both structure and the behavior, definitely ensures runtime safety. We can implement in this to ensure runtime safety. However, we were talking about the static checking in which the runtime aspect was not there, but we can make it so. We can improve the expressiveness of the program by features like operator overloading. I mean, these features like operator overloading can also be incorporated, but there we have to specify that this operator plus will not get operands as the way it was supposed to get. They can get operands the way the user wants. So for example, we know in C++ we can overload an operator plus, where I mean, ideally this operator plus should have operands in the form of numbers. They can be real, they can be integer, but we can also make this operator plus to work on strings. So that aspect we call operator overloading. So those features can also be incorporated by defining some proper type systems. Improve runtime efficiency by generating better code, for example, multiplication when one of the operand is 0. So those optimizations can also be done. A type checker verifies that the actual type found in the program matches with the expected type. So this is a one-line short explanation of what we are expecting to do. It actually tries to verify that this is what the type should have been there for this operand or for this construct, and this is what I have achieved. So are they right or not? This is the simple thing that it can, the simplest of the thing that it can perform. As an example, add operation in C expects the observed types of operands to be integers or numbers. But let's say I mean, the specified type is a number, and we're not giving it a number. We're giving it some character or string. So that is something that should not have been the case. So such cases should be immediately reported by a type checker. So a type checker actually implements type systems. A type system, again, we can refine the definition by saying that it is a set of rules proposed for constructing new types from the existing type. It gives a method for determining if two types are equivalent or compatible. We can formulate such things as well. Set of base types or basic types can be like integer, character, void for representing null, real, float, etc. Its specification may be done using a syntax-directed definition. So we can write an SDD or an SDT to specify the type system that we want. So there are two known basic types, or the way we define these types. We have got basic types, we've got constructed types. So basic types are atomic types. that do not have an internal structure. For example, Boolean, for example, characters, numbers, void. So these are the basic types actually. Let's say we are saying the Boolean operations that we are saying, the numbers, and then we having the operators like, I mean, the operators that can be there on these numbers can be plus, divide, minus, add. So all these are all these mentioned over here are the basic types. Constructed types are also known as the user defined types, are the types that are constructed from the basic types and other constructed types. For example, int A10. So this type actually is an array. I mean, we say that this A is an array. We do not no more say that this is an int. So we say that it's an array of integers. So it's having 10 elements altogether. So it's an array of 10 integer elements. So this is a type. If I mean we specify over here, then array is a kind of type that we are referring to this situation. But this array type is actually coming from another type that's called integer. So it's actually a constructed type or a derived type. Okay, so the type of any programming language construct will be denoted by a type expression. Type expression could either be basic, integer, character, or what we were talking about, or formed by applying type constructors to other type expressions. All basic types are considered as type expressions by itself, and a type name is also considered as a type expression. Okay, so type constructors. Type constructors are defined as so that can be applied to type expressions. It can be an array written something like this in a more generic way actually. This is not the very way we might see in languages that we very formally understand like C, C++ or Java. You might not find it written like this, but it's a very generic form. We can say that there is a constructed type A or array written as I, T, where I is actually the index, the amount of numbers that you want, the amount of location that you want or cells that you want in an array, and T is the type of each of them. So if T is the type expression, this T is a type expression, then array written as array I T is a type expression where I is the index and T is the type. For example, in this very generic way I can write it int a 10 comma int, where it means that there are 10 elements and each element is having a type of type T, a type int. Another construct that we can have is functions. It maps elements of one set to another set. For example, we can have a function where the elements are p comma r and their type has been defined as int, and it returns an integer type. So this is the return type that we mentioned. It's written in a very generic form, not exactly the way we are more familiar with functions, written as something like int. Then the signature is slightly different. So this is a more generic way of writing them. Function f, the arguments p comma r, and followed by the type that these arguments have and the return type actually. So this is what is being specified. I mean, this is a function f, and this f is actually having a type of function where there are two integers being passed on, and the return is a pointer type, that too of an integer type pointer. Another constructor that we can have, a type constructor, is a pointer. Pointer t written like this is actually a type expression if t is a type expression denoting that the type pointer to an object t. So we can have, we can have something like this. This is more familiar to us. Int star p. So we say this is a pointer p, okay, and that too of the type integer. But it's derived, and a more right type that we say is now this is being an integer. This is now more of a pointer and then an integer. So these are the various or some of the type constructors that we actually use to form some new types from the well-known basic types. Okay, so type checking can be, as I was saying, it can be at the compile time as well as it can be at the runtime. Strongly typed languages, it's a new statement that we have added on. All inference and all checking can be done at the compile time. Statically typed or static checking refers to an implementation that performs all type checking work at the compile time only. The strongly typed languages are dynamically typed. That means, the moment we have the word dynamic, it means it has a relation with the runtime situation. So strongly typed languages are dynamically typed and are dynamically checked. So if you are performing type checking even at the runtime, then those languages can be referred as to strongly typed languages. Strongly typed languages, statically typed languages with dynamic checking actually. For example, Java is one of the most commonly known strongly typed language. Performs some type checking at the runtime also. That is, some sort of an execution level or modeling is also there. Because of which we get something known as a runtime safety. So strongly typed languages like Pascal, Java, they ensure runtime safety as well. Language implementation that guarantees to catch most type related errors before they execute can simplify the design implementation. Although the language that we normally find or at the undergraduate level that we more encounter is C language, however this language is a weakly typed language. Majority of the type checks are done at the compile time. And then we also can have something known as an untyped language altogether. The assembly languages are untyped languages. And if you recall well, then we do not have those type descriptions at the assembly level. I mean, we do not write those int or char or float or array or nothing like that. There is no such kind of a type specified at the assembly level. So we have absolutely untyped situation at the assembly level. C is a case of a weakly typed language. However, Pascal and Java are strongly typed languages. So the moment you get something, the moment you get this phrase of weakly typed, so you can recall this to be something like checking happening only at the compile time. And when you say that this is strongly typed language or strongly checked language, then you can just recall and think about that this language is actually double checked. The more check you have, the more stronger you get actually. So you are being checked at the compile time as well as there are certain checks at the runtime as well. Okay, so type checker, different type systems can be used by different compilers, static and dynamic type checking of the types. Checking done by the compiler is said to be static. Checking done by the target program when it runs actually is dynamic. A good type system attempts to eliminate dynamic type checking as much as possible. Definitely, it's not always possible to perform all those dynamic checks because that will be an added overhead onto the program. You'll have to put all those code into it. So it's better that we have as much as a minimum amount of possibility for dynamic type checking, and we would like to finish a majority of our task with static type checking only. But that is the aim that we wish to accomplish. A language is strongly typed if the compiler can guarantee that the program it accepts will execute without any type errors. There won't be any type errors at all, whether you're running the program in any situation. It will have the minimum or absolute no type error. So such kind of a language cannot. So we are having multi-dimensional statements pointing towards a language being strongly typed and pointing towards a language being weakly typed. So weak type checking, in such cases, type errors can lead to errors calculations. For example, Ruby, that's another language of as an example, and strong type checking, as we can see, it's an example like Pascal. Static typing or type checking or strong type checking, types of all expressions are determined the compile time before the program is executed. The type check is typically carried out in an early phase of compilation. So actually, again, we're talking about the fact that majority of the things that could have been done at the runtime are being solved at the compile time as well. So we're talking about those aspects also that may come during the runtime of the program. A type checker verifies that whether the type of a program construct matches the expected type or not. This is the global aim. Actually, we are moving towards defining a simple type checker. So that's why we are getting these statements again and again. Operator star or the operator star, that means a multiplication operator in C requires integer operands or operands of the type numbers. They can be float as well because we've defined rules for those as well in this definition. Index of an array must be an integer, absolutely. That's another thing that we need to check, that the index of an array A20, A30, we do not have AX where X is a character. That does not specify anything because we need an index. An index can also be a number. Forget about being character. That index cannot even be a float or a real value. A4.2 does not make any sense to the system. So that has to be an integer only. So those checks are also to be performed. Also that the indexing is applied only to an array. So we are not applying indexing to something else, let's say a function or any simple variable. We are applying indexing to a variable. That does not make any sense again. So it has to be done only to an array. Okay, so the position of the type checker, as we can see graphically, we have the parser which is generating the parse tree, not by itself but by the help of certain rules semantic rule that we have embedded over here. I think we have already discussed about this part. So we're getting the series of tokens to the parser. The parser, along with some semantic analysis, generates the parse tree, and then on this parse tree we apply type checking. So here the type checker lies. It is something after parsing has been done and some sort of semantic analysis has been done, and before the IR generation is about to begin. So if you talk about the input to a type checker, it's a parse tree, and if you talk about the output to a type checker, it's again a parse tree. Or rather, I would say a much more well-defined annotated parse tree will be an output, and the IR generated over here will, let's say, be a tag or 3 address code. Type information is needed by the code generator to ensure the target code generation process is correct and efficient. If I do not have the type information, then the correctness of the program to which it has been converted cannot be guaranteed. Consider the following cases: operator overloading a symbol that represents different operators at different locations in the program. I mean, it's just trying to say, let's say we have operator overloading. In that case, the plus operator can have different meanings at different locations. At times it is an operator that is trying to add 2 numbers. At times it can be an operator that is trying to perform some operation on 2 strings, because we have given the freedom of operator overloading within our program. So we'll have to check all those things. At this very time, is it an integer related operand? At this very time, is it a string related operator right now? So we'll have to do all those things. We will also have to face challenges like polymorphism. Languages that have these properties as well should also be tackled. It is different from overloading. Polymorphism actually refers to a more generic case where, for example, operator overloading specifically to operators, whereas polymorphism can also talk about function overloading, where a function having the same name but has different arguments, and even if the arguments are same, they may be having different types. So such of the cases will also be considered, because over here we have defined that function is also a type, and then we are providing parameters to it. So we'll have to check whether the parameter provided, because in that case we'll be having 2-3 occurrences of the same function. For example, we have a function sum. So we are having sum a comma b. Fine. So this will do a sum of 2 numbers and it may return a value to you. But then again we are having within the same program sum a comma b comma c. And now this sum having the same name, almost a similar signature, but now is having 3 arguments a, b and c. So this has to be checked whether which of these sum is actually being referred to. So it's not just that operator overloading is a challenge, but features like polymorphism also pose a greater amount of challenge for type checking purpose. So where does it all start actually? Type checking, it all started from the declarative statements. If you remember, we also talked about declarative statement when we were talking about semantic analysis. So those are the first lines in our programs that actually tell us a lot about type. We say int a comma b, that means type of a is integer, type of b is an integer, and we said that for this purpose of analysis we have specified rules. So here are those. This is the same slide. So just to recall, because this is the very process this is the very phase from where type checking actually originates. So the first of the statements that we'll encounter in our program, or the initial of the statement that we'll encounter in our program, will be declarative statements. So D derives TL, and we have discussed all these semantic rules, and ultimately these semantic rules, they help us in understanding the type. So the attribute type is evaluated at each node, and the obtained values are submitted to the symbol table. So whatever type we are getting of these IDs, they will be submitted to the symbol table, and then once submitted to the symbol table, they will be utilized in during conversion or during type checking of expressions, because these variables that have been declared in a declarative statement, they will be utilized in expressions, they will be utilized in statements, and then their type checking has to be done. So those type checking instances or those type checking references will be done on the basis of these inputs that we have done to the symbol table. A very simple example that we talked about in the last lecture, at int id comma id comma id. So this was the parse tree that we got, and ultimately we said that this will be an inherited case, and the type will flow like this and this and this, and ultimately we will have the type of this id, this id and this id, and immediately we will make an entry to the symbol table. So it means that once a declarative statement of this type has been executed, the type, if it is compiled at least, then the type of these identifiers are also known now, that the type of this identifier will be this and this and this. So immediately at the compile time only, no need to run the program. We're not talking about runtime at all. We're simply saying the moment this statement will be compiled, we'll understand or we'll come to know that type of this ID and this ID is what, and we'll put it into symbol pill. Why? Because these IDs or these identifiers will be used in expressions, they will be used in statements, and then we'll be requiring these types that we have stored. So now we'll write a type checker that will extract the type information for an expression, for a statement, and then we'll have the type information for the entire program, because the program is nothing but a sequence of a logical sequence of statements. So we'll have the we'll have a type information for the entire program. So we'll just write a type checker for that very purpose. So just trying to implement a simple type checker. A type checker is a specification of translation schemes. It synthesizes the type of expression using the type of its sub-expression. So you can see this is a similar kind of grammar that has been specified. P derives DE, D derives D or D, something related to what we have just seen in this slide, something similar to it. This will generate actually the types, or D derives IDT. T derives char, integer. I mean, whatever new type you want in your system, just add over here and give a proper semantic to it. That this is what it will mean, and that type will come to you. For example, over here, no type, let's say float has been mentioned. Simply mention a type float. No type over here has been mentioned, let's say string. If you want something, some type like string, then simply add it over here. Add a type string, and you'll get. I mean, you'll also have to write the proper semantics to it. You'll have to give proper meaning to it. And similarly, we can have expressions like literal, num, E derives some literal, E derives some number, E derives some identifier, E derives some operation E mod E. It can be a mathematical operation, an arithmetic operation, it can be a logical operation. Okay. Okay, program generated with grammar include integer, they may include something like this, key mod 211, 2011, array 256 or character. I mean, these are the things that we may find in our program. We'll do an example in which we'll deeply describe about these components. So initial part is similar to what we have discussed. D derives ID T, T derives character, T derives integer. So just simply feed into the system that the type of this is this. One thing important that we can see over here is array has also been defined. Like in this system, that the system we have imagined or we have just talked about for as an example purpose, it says, let's say array is also defined as a type. So array num of T, this is the way we write it. Let's say, so type over here, T dot type, the type of this T will be referred as to an array type of I, that is a number, and its value actually. So 1, 2, 20, 30, whatever value has been specified over here, that will come at this position, and T1 dot type. So whatever type we have over here. So this has this rule will actually give the type array to this T, because this will get a type. This integer will give a type integer to this T. This character will give a type character to this T. You have some float, put up this production, add that production, and give a rule for it. As simple as that. Another example given over here is for a pointer type. So written, let's say like this. In our case, we normally know that we use a star operator. We use a star symbol to represent pointer type. So in this case, let's say in a very generic way, this symbol is being utilized as the pointer representation. So we say that the type of this T, the rule has been given, the type of this T is pointer T1 dot type. So it's a pointer of T1 dot type. So it can be an integer pointer, character pointer, or anything like that. Okay, so type checking for expressions. These are the two things we'll find in a program so openly. We'll find statements, and statements will have expressions. So we need to understand how type checking for expressions will be done, and we need to understand how type checking for statements will be done. So first of all, we need to have a grammar. We just take a very simple grammar. E derives literal, E derives number, E derives ID, E derives even mod E2, where mod can be any operation, arithmetic operation in our consideration right now. It can be some other operations. We'll have to define proper rules for it. And E derives E1, and that too we are taking a case of it being a pointer. So in the first of the cases, E derives literal, that is the type of this E is character simply. E derives num. If this is the production, then type of this E is nothing but integer. Let's say in our very simple case, we're talking about number being only an integer. If you want it to be float or some other type, we'll have to define properly a rule over here. E derives ID. It means there's an identifier in our program, and it's not a constant, it's not a character specified, it's simply an identifier. And if it's an identifier, if I'm having an expression that is being converted to an identifier, then in that case the type of the identifier will come from the symbol table, because this identifier must have come in a declarative statement, int a comma b comma c. So a, b, c have already been declared, and from this statement its type must have been calculated. So its type is now present in the symbol table. So that is why we are having a rule over here that e dot type is equal to lookup. We're not declaring what type it will have. We're not saying it's integer or character or float or anything like that. We're simply saying go to the symbol table, look at this entry of following to this identifier, and whatever type has been mentioned, that same type will be of this type E. So if we are having a subtree, or if we are having a production of the type E derives identifier, then in that case, whatever type this identifier is having, this E will also have the same type. And the type of this identifier will not be calculated, but it will be referred from the symbol table, which was kept earlier, which was calculated earlier and kept over there. That is why there are some languages, for example, C. In C, we say that all the declarative statements must happen in the beginning. Whatever declaration you have to do it in the beginning. Then we got some relaxation. In languages like Java, there's no such compulsion that you have to do in the beginning part of your program, there should be only declarative statements. It says that anywhere where you want, you can declare, but the condition is that before utilization of the variable, a declaration must happen. So if a variable is being used in an expression or in a statement, then in that case, even there, a declaration must have preceded this. So there's never going to be a case when a variable has been is being utilized but has not been declared. If that is the case, an error will be generated. It will not find a corresponding entry in the symbol table for it. So that is why we normally find that error also. The variable being used has not been declared, or an unknown variable or undefined symbol. We normally find this error. It's actually referring to the same fact that it tried to search the symbol table for an entry to it, but could not find an entry. Okay, so if we have, let's say, an arithmetic operator, let's say plus, minus, star, divide, we have those operations, then expression will be something like this: E derives E1 mod E2. Then we'll write a rule pretty smartly. We'll say that E dot type, the type of this E will be, now we're living into it here, we're saying if E1 dot type is integer and E2 dot type is integer, then its type will be integer. So we're adding a condition to it. We're not giving it a type directly. We're simply saying if E1 dot type is integer and E2 dot type is integer, then it is integer, otherwise it's an error. However, we know that in our languages we also allow arithmetic operation on on real numbers also. 4.2 plus 2.2, that is also allowed. In that case, what they must have done in that language, whatever language we talk about, in that language, this else would have been extended to an else if, where this would have been extended. Rather than simply writing type error, we must have written over there that if this has happened, then else if E dot type is real and E dot type is real, then the type of this E will be real. If you want to add multiple combinations to it, for example, we want the first type to be the first of the component to be integer, second component can be allowed to be real, or the first to be real or second to be integer. In that case, what all we need to do is add rules, proper rules after this. Keep on adding whatever you want to specify, and somewhere or some combination that you do not want, simply end up with a type error. So if you do not want a character to be added to a float, let's say, so put up all the combinations and leave that combination left out will be simply a type error. So in all those smart languages that we work nowadays, where characters are also being added, where float are being added to float are being added to numbers, and numbers are being added to integers are being added to float, and integers are being added to characters. In all those smart situations, this rule has been modified. It has been extended. It's a very simple rule that is being shown in this slide. It's a very simple rule talking about one single simple scenario. You want more scenarios in your language, add up to those, add those possibilities and extend this else to an else if situation and keep on adding all those rules that you want to specify. For example, you do not want a float to be added to a character at all, either being E1 or being E2. A float cannot be added to a character. In that case, you simply omit that in any of these conditions, and simply this else type error will handle that, will handle that situation. So this is how we have done. So in all those languages where we get these smart operations happening now all together by itself, in all those cases this rule has been modified. So you dream about any of those situations, just add up a rule over here. Similarly, a rule for this e derives pointer. E dot type will not be expressed right now. A condition is there. If E1 dot type is a pointer, then we say that the type of this E is a type that that pointer had. Not E is not having a type pointer. Even E is having a type T, the type of the pointer. Otherwise, if this is not a pointer, then it will be an error in that case. So this is how, I mean, you have more expressions in your language. For example, one expression that has not been specified over here, that can be a Boolean expression, where we try to compare two components as far as the condition is concerned. For example, A greater than B, that's also an expression. And I mean, similar kind of a rule can be specified. The way that we have written a rule for this, we can specify the rule for that also. In that case, we will say if E1 dot type is integer and E2 dot type is integer, and the operator being performed over here is a Boolean operation, then the return type of this expression will be Boolean. Over here we are saying it will be an integer, but then in that case we will say that it is Boolean. So expressions that we have in while E do S1, expressions that we have in for, the conditional expressions, expressions that we have in if, expressions that we have in all those situations will actually be having a type of Boolean rather than having a type of integer. If we want that even on integers those statements can work, then we will have to specify those types similarly. Okay, so we can quickly move on to type checking of statements. Now, till now we have talked about expression. Now we are talking about statements. Now look at this. The most basic of the type statement that we have is assignment statement. Majority of our statements found in a program are normally belonging to this category of assignment statement, written of the type A equal to B plus C divided by some arithmetic situation. So it originates from this kind of a production. S derives ID equal to E, where on left hand side we do not allow an expression, there is an identifier. However, on the right hand side we allow an expression to be there, and an expression of arithmetic type. So it's saying that an expression may be having a type, but a statement altogether will have a special type. It will not be int. A statement cannot be int. A statement cannot be float. A statement cannot be character. A statement will have a special type referred as to void. Okay, so the statements that we have in a program, they carry a special basic type called void. So I'll say that definitely if ID equal to E is a statement, this will have the type void. I do not have any problems with it being void, but I'll not give it directly. I'll say that, I'll formulate a rule. I'll say that S dot type, the type of this S, will be void if ID dot type is equal to E dot type. Okay, so whatever type you calculate, because in the previous rules we have given how the type of expressions will be calculated. So what will be this type of E? We have given the rule. So run that rule, find out this type, look in that symbol table for its type, both their type should match. If it matches, then this S or then this statement will have a type void. It's a very simple rule, pretty simple to understand, and its dependency has been smartly shifted on ID and E. So if you have a situation where the left hand side type and the right hand side type do not match, then in that case we'll simply say that the type of this statement is not void, it's an error. Same has been specified in this rule. S dot type is equal to, it will be void if this happens. It will be void else this will be in type error. So the answer comes from this parenthesis. However, another statement that we can have in our programs is an if statement. If E then S1, where E is referring to a conditional expression and S1 is again referring to a nested body of if. So we can have, again within that if, we can have assignment statement, This S1 can be again an if statement. This S1 can be a while statement. This S1 can be a do while. It can be a compound statement. It can be anything, but it will be a statement. And if we remember the trick, if it will be a statement, its type again will be void. So the type of if statement will be void. The type carried by a while statement will be void. The type carried by a do while statement will be void. So even in the body, if we have written a while, so having an if, within that we have a while, so the type of while will be void and the type of this if will also be void. But we have to do it smartly, because the parent block, if the if statement block is the parent block, and then we have a nested situation of having a while block. So any type error that happens in this while, its effect should be there on the type situation of the if also. So the child block or the nested inside block will affect the type of the parent block as well. So we have to specify a rule so that all these nested scenarios are also considered properly. So look at this, we have written this rule pretty smartly. We could have said s.type is void, we could have said that, but we're just putting up some smart conditions, and we're saying that s.type will be calculated if e.type is boolean. The type of this e will be boolean, so it has to be a conditional expression. This cannot be an arithmetic expression. If you want an arithmetic expression, we'll have to define a rule for it. So if e.type is boolean, then s1.type. So it has smartly shifted. It's not saying that if e.type is boolean, then void. It's saying whatever type you calculated for s1, that type will go to s. If it was having an error, this will have an error. If the inside body component is having an error, the nested outer body will have an error. If the inside component is having a void and your condition is boolean, then it will be void. No problems with that. So we have smartly shifted the type checking component consideration onto the inner block. Same goes for while. You can see simply while e do s1. So if e.type is boolean and s1, then whatever type this s1 is carrying, the same type s will carry. Again, we can simply write a similar rule for do while, do s1 while e. Whatever type carried by e will now be carried by, whatever type carried by s1 will now carried by s if e.type is boolean. Then we can have compound statement as well, s1 semicolon s2, to represent multiple statements within that. A quick example to cover up all this what we have studied. Let's say we have a variable, we have a statement int a comma b comma x comma y, and then we have a code snippet something like this: while a greater than b, b is equal to x plus y, and x is equal to x divided by, just random code snippet over here. So we can have a simple parse tree for that has been constructed by this grammar, the grammar that of statement that we have just talked about. So this is the parse tree that we will get, and you can just verify this parse tree. This will be while e do s1, and you can see that of each component I have tried to identify the type. So look at this point, e.type is boolean if this is integer, this is integer. This e.type will be integer, and this is integer by the rule s derives id equal to e. If this is integer, this will be void, so it has been kept as void. Look an example over here, id.type. So id, if let's say it was integer, we have specified here that all these variables are integer. So if it is integer, this is integer, e.type is integer. If id.type is integer and e.type is integer, remember this first rule, id.type and e.type, if they match, then it is void. So this type is integer, this is integer, and ultimately this is nothing but void. Similarly, we keep on calculating, and the entire code snippet is now having the type void. So this is how the type checking actually can be done on such code snippets. So just to conclude that we have done our discussion on type checking, type checker, static and dynamic type checking. We have discussed about a simple type checker, type checking on expressions and statements. In the upcoming lectures, we'll start discussing about intermediate code generation, and almost we are end on to the semantic analysis.
With this note, thank you, sir. Thank you very much for giving a precious time, and definitely by tomorrow we would be starting with the intermediate code generation. Thank you, sir. Thank you so very much.